good afternoon, or good evening, depending where you are from this small planet. I welcome you to another webinar of the webinar series for the core modeling activities. I am pleased to announce our today's speaker is Professor John Pomeroy from University of Saskatchewan. Professor Pomeroy will update us today about the latest development in the next-gen modeling theme. I am personally very excited to hear the recent development in this theme. I was always wondering myself personally, what is next-gen about it? And since I'm a little bit more involved and see the development, I should say it's a very beautiful and interesting process of exploring science by pushing the envelope of latest computational hardware and softwares at the bleeding edge, which hopefully will help us capture and mimic the complexity of the real world processes, which I'm sure it's John's passion as well. Before starting, I would like you to thank you for joining this webinar on behalf of the core modeling team, Professor Art Petroniro, Professor Martin Clark, Joy Mitsugiani, and myself, Sherman Garari. I hope you enjoyed the webinar. John, the floor is yours.
Okay, thank you so much, Shervan. Of the things I do in Global Water Futures, the next generation modeling group that I lead is the fun thing that this makes it very exciting to get up in the morning and to keep working late at night. And so I'm really happy to talk about the advances made by several people in here. I'm going to be featuring work from Chris Marsh, Kevin Green, Kevin Shook, Joseph Lukili, Abbas Fayyad, Walter Nobin, and then of course the many faculty members that work with them, and make reference towards the future, which will be data simulation for prediction with the work of Jabang Liu. So we'll jump right into it. There's lots of material to get through here, and it's very, very exciting indeed. The first, just to remind everyone what the next gen modeling is about. The objective is to develop systems that will enable flexibility in spatial configurations and process representation, whilst using modeling coupling methods and parallelism in computation, so we can take full advantage of high performance computing capabilities. And we have some very nice ones in Global Water Futures through the Copernicus system, for instance, or through our Compute Canada accounts. We want a system that is scalable and applicable from the scales of agricultural fields, ponds, mountainsides, forest stands, slopes, small basins, right up to continents. We want a system that permits multiple representations of hydrological processes. This means it needs to have some modularity to it. And that allows for hypothesis testing within the model by looking at different configurations, but also something that Martin Clark and Al and I have found over the previous decades of research is it allows us to rapidly advance hydrological modeling by plugging in the advances of a graduate student or postdoc or some other experiment as a better evapotranspiration process model or a better infiltration equation or things of this nature. And because we're in Canada, we have to pay special attention to cold regions processes involving frozen forms of water. We want to take advantage of the new atmospheric forcing data, the geospatial intelligence work, the model agnostic modeling workflow advances in Global Water Futures, and be ready to couple with new advances in modeling glaciers, river ice, water quality, water management, and hydroeconomics. And I should mention that we're working in parallel on demonstration of the forecasting capabilities of the next generation system, which are substantial, and further steps there will involve data assimilation into that. So some of the personnel on there, I think we've got most of them through the authorship on this, but noting the faculty leads, the various postdocs and scientists associated with this, and very important international collaborations and national collaborations through Environment Canada, University of Washington, and Edinburgh University, and then links with the core computing team in GWF. So little bit of the old background on the Canadian hydrological model. You might have seen this before, but that's okay to refresh ourselves. And so it uses right now unstructured triangular meshes, which depend on topography, vegetation, soils, and hydrography, other aspects. It has a flexible structure, so we can test multiple hypotheses. We can incorporate existing code or write new code for it. And it has already built into it a number of algorithms which allow for fine scale downscaling of numerical weather prediction model data or other data. So right now down to 50 meters. So taking a 2 kilometer or 2.5 kilometer atmospheric model resolution right down to 50 meters, which makes hydrology very local. And that's where the action is sometimes, particularly with extreme events, as we've seen in BC. So the accounts for a lot of the mountain processes, which are the most complex ones we have to deal with: the slope and aspect, the shading, redistribution of snow by avalanching and blowing snow, canopy, forest canopy interactions with snow or rain on snow, energy balance, snow melt, infiltration of frozen soils, and more. And we'll see how much more it has now. Here are some of the process representations that are in CHM currently. And then I'm going to adding a few here to call your attention to. Many of these you've seen, but the hysteretic and gatekeeping depressions model, I'll talk about that in detail today, based on recent advances from Kevin Shook and colleagues. Incorporating the hydrology, bringing Summa into CHM, which is a very exciting development. And then the ModFlow additions to CHM, which is coming, and we'll also talk about glaciers, which are coming. So first are some structural updates on CHM. Of course, having that platform functioning properly and fast is absolutely crucial for our forward progress, and a lot of the efforts go on to that. So it's not something glitzy that you'll see out on the screen, but having that, having it working properly on Copernicus and various architectures is crucial. So checkpoint capabilities have been added and optimized for the various architectures in the program. Internal variables have been separated into states and fluxes, and that's carrying on. And the coupler formalization is ongoing. We talked a lot about the multiple granularity coupler last time, which will allow us to couple blocks of modules, like bringing in something like Summa or a piece of CRIM on soils, or allow us to go right into individual equations and short algorithms to deal with. And so we needed all this to make CHM ready for data assimilation and to improve its performance, which we're testing in parallel as the Snowcast product, as a demo product. The performance improvements are substantial. When we add a pre-processing step to CHM that partitions the meshes based on the MPI ranks, we get a dramatic memory reduction that enables more MPI ranks per node, better computer usage, and we basically doubled the number of MPI ranks, which provides a speed up to so it's twice as fast now. And so kudos to Chris Marsh and Ray Spiteri and Kevin Green and others who have worked on these elements and advanced it considerably. We find that wind fields are important for blowing snow. They're important for evapotranspiration, and they're really difficult to sort out in complex terrain. We've known that for decades. But there's been great advances with the wind mapper and corrections of that. So we start by generating wind flow simulations with a computational fluid dynamics model, Wind Ninja, at 50 meter by 50 meter resolution. That gives us a wind speed up map for a number of directions, n number. And then we apply Adam Winslow's parameter correction to identify leeward recirculation zones where Wind Ninja wasn't working so well. This allows us to calculate the snow drifts a bit better in the lee of mountain ridges. And then we can pre-calculate the wind fields. This gives us a 100 times speed up versus the online wind flow simulations. So it's absolutely essential. And these improvements have allowed extension of Snowcast into larger domains that we'll see later. There are issues with this. You have to issues of lining up our cells, the alignment of these grids is not trivial, and you have to merge them at large spatial extents. So going continental is not as easy as we might have thought at one point. But we can certainly do this and merge and create wind field subdomains over very, very large areas to create the model domains. So I'll show you in a bit. That's over central to southeastern BC and western Alberta that we're seeing from the US border up to Jasper, up to the northern end of Jasper National Park. The mesh generation improvements are crucial for it. There are different error tolerances, and they have different impacts on the mesh generation. And so setting those tolerances is important. The mesher generates triangles that ensure the triangles represent the underlying topography and other attributes such as vegetation, soils, hydrography. So we're conforming these triangles to simple shape files such as rivers and making sure they do not cross features such as rivers and creeks and others and represent them exactly. And I'll show you what that means. So it's easy to do this in the mountains because you know where the rivers are, they're in the valley bottom. And that's absolutely fine. But when you get out to the prairies, it's not quite so simple. And that's where we want to go. So here's an example of the Battle River crossing Alberta and Saskatchewan, joining the North Saskatchewan at North Battleford. And now we can handle these very complex cases that we get in the prairie landscape. So Battle River is 45,000 square kilometers and 27,000 triangles. So there's the triangles laid over it, and you see we're taking into account the drainage network here in a realistic way, which is important advance. And the interesting looking at triangle size distributions. The maximum triangle size is big in some cases, 110 square kilometers, but the average one is closer to 1 kilometer. So we'll need to keep breaking these up still based on soil polygons and more detailed vegetation maps, as well as some of the taking into account some of the larger wetlands through here. But we get some very small triangle sizes in this distribution. But it enables us to go to large extents. And so this is setting up the measure for CHM over a vast area from southeastern British Columbia up into the Northwest Territories to Great Slave Lake and down into Montana and North Dakota and Washington State, and then as far east as Manitoba. So now we can really start looking at these continental scale applications and just showing you how the triangles might look in an environment like that. Now, there are going to be issues of subgrid representation, subtriangle representations that we need to work out. We're probably going to need hydrological response units within these triangles, and we're still working out exactly what to allow those HRU to do. They certainly would have be each a control volume. They would have horizontal transfers between them. We'd also be looking at statistical representations of subtriangle variability. And this one, you can see Calgary here in the center of the image and then moving east onto the prairies from the Rocky Mountains. So that prairie representation is always going to be a challenging, though we think of them as flat. They're not really that flat, and there's lots of topography in there that can guide this. This is around the Capel River Valley in southern Saskatchewan. You can see, but we also have summer convective storms to deal with, and so we need to have grid cells that are corresponding to our forcing meteorology. If we're able to drive this with 1 kilometer gem, that we do not want any triangles that are larger than 1 kilometer. We want triangles that are smaller than 1 kilometer, and we have soil polygons which available with the prairie region, which give us lots of spatial complexity, cropping patterns from remote sensing, vegetation such as shelter belts, copses of trees and others, some of the larger wetlands that we want to resolve explicitly, the prairie creeks, and of course settlements. And what's happening in the towns is always of interest. So that's we'll continue to work on that, and I'll talk more about this with respect to how we split up the representation of wetlands between explicit and statistical representations in WGDM later on. let's jump back to the mountains though and think, what are we going to be doing with glaciers? And here's some of the work that Abbas Fayyad is looking at. And of course, we will need to have that high resolution meteorological field that CHM can produce, as well as the topography and glacial surface situation for the boundary conditions. And this is just showing the research sites at Pato Glacier from our research station on the ice, and you can zoom in and see there's actually some people there working on the station, and then our hut off to the side. That hut is where the edge of the ice used to be, by the way, back in the 1960s. So, so a possible glacier scheme for CHM would have a multi-layer snowpack above it, multi-layer fern. Fern is old snow, multi-year snow, and then fern slowly turns into ice. And so as the fern ages and densifies, it would eventually become ice layers, which would track as well down to bedrock. And then we'd be routing water through these, through the snowpack, through the fern, through the ice, as well as calculating the snow redistribution, sublimation, and melt above this. So, so in the glacier component, we'd have the snowpack, fern, ice, and glacier dynamics in there. This ice is not stationary; it is moving, and we had to calculate that. But the time scales are very much slower than for the other processes. They tend to be something that can be updated as a state for the system once a year, or we could within a year, and we have to make those decisions yet. So it's thermodynamics and mass processes within the snowpack, fern, glacier, ice, and then the hydrology becoming more important as we get down into the fern and ice components. And so we've learned a lot modeling this with CRIM through the work of graduate students such as Jirez Pradinanga and Caroline Aubry-Wake. And we've learned quite a lot about large-scale glacier modeling with mesh, with the advances that have been made in there by Abbas and Yosef and Mohammed and Zalalam. And so we'll be bringing these together with other advances as we develop CHM glacier components. And just a visualization of what this might look like with the snowpack, fern layers, and multi-ice that Abbas has put together for us. And of course, we'll be tracking the liquid water and the temperature evolution through that system. Okay, let's jump to the hydrology. And this is an exciting development that Kevin Green has been working on in collaboration with Martin Clark and his team, such as Walter Nobin and many others, is bringing some hydrology into CHM, basically the land modeling components that are needed. And so the first step in that, there will be other steps, but the first step is to couple Summa hydrology to CHM. And so this is to enable the energy and mass calculation components from Summa and implement these in the CHM triangulated meshes. And so Summa, Martin Clark developed this about 6-7 years ago, the structure for unifying multiple modeling alternatives. And so it's a modular system with internal solver for solving of differential equations. So we want to implement this. It is computationally fast already, and it is very strongly physically based, has had extensive LAF tests against some classical hydrological purposes. We want to highlight the design of interface for Summa within CHM, and then also begin to pull apart Summa in the future. So, but first is, can we force this? And so, you know, we look at different forcing things as a bit of representation of Fortress Mountain with our weather stations, or the gridded representations that we can see. And the so CHM can use its station and forcing data routines to drive the Summa for CHM modules. And so there's a JSON configuration which allows this to be done, and we manage it through texture and netcdf files. So the and then Summa can manage its own forcing data if we need it so it allows us to intercompare things as well. Here's some of the data flow for Summa for CHM. CHM manages control the simulation. It's sort of the master of the simulation, and Summa for CHM is implemented as one large module for now. So it's not broken down at this point, though we will get into that further. And the how Summa is configured is handled from within Summa through here. And state variables need to be passed between the CHM C++ and the Fortran of Summa. And there's some ugly bits behind the scenes, but an easier to use interface in here. And so we're transferring, forcing prognostic, diagnostic fluxes through here. And they're passing into the interface. So this interface is actually crucial. And of course, we want to verify, is this working properly? And the first thing you do is you take a model like Summa and you take a selection of modules from that to create a Summa model, and then you see if we can get the same sorts of results from this model in Summa standalone versus Summa within CHM. And so some of the classic problems called LAF tests that Martin put together a few years ago involve water storage and transmission in soils and thermal, dynamic, and hydrological processes in the snowpack, going back to Colbeck's model, cryosuction processes in frozen ground. And so we can compare these. And so some of the results, Celia was unsaturated flow, Miller was variably saturated flow, and Vanderbroek with a two-layer modeling flow. So let's take a look at some of these, and they're encouraging. The results are numerically identical between Summa for CHM and Summa. And so remember, we're just comparing two models, but we are showing that we're able to duplicate the Summa runs accurately here. And the LAF tests that were done with Summa were able to duplicate things such as the looking at analytical numerical solutions for ripe snow depths and refrozen snow depths, fresh snow depths, things like this, water transmission and storage. And so this is comparing depth to pressure head for various simulations, water entry into soils under different pressure heads and different soil textures, water interfaces. This is a classic hydrological problem, sand into loam, and getting the matrix heads profiles, matching them quite nicely. And then the cryosuction, what to do with volumetric water under cold freezing conditions. And you see that changing there. So we're able to simulate that quite nicely. And that's a tremendous advance, I think. So for the future, we have to do a bit more hydrology than one dimension. And that involves bringing forward lateral LAF tests, Wigmosta's model being one where we move beyond vertical columns and look at nonlinear columns. So these are some of the Summa tests that have been done. And these are the things that we wanted to match here. And also finer grain control over the subcomponents. So this means explicitly separating out CHM models with Summa models, pulling out the Summa bits and coupling them with other bits that we're talking about. Blowing snow, you know about, but frozen soils and permafrost is another one that we can compare. HDDM, mod flow, we'll see more of this here today. Okay, so model coupling in CHM requires efficient model configurations, and so when we start to bring Summa and CHM together, we'll need to route it, and Mizu route is an excellent advantage of this. We can look at some hypothetical examples in here, and this is some of the work that Walter is working on, and there's an example from Chris's work of the representations that we'll need to apply this on. So, but first, it's important to look back to Summa and to look at the efficiency of its model configuration. And it is an efficient and reproducible large domain model configuration that's possible here. This is Summa set up with its HRUs and GRUs within it with Mizu route. And so a tremendous number about 500,000 model elements at about 33 square kilometers for the continent of North America, and able to do 40 years of hourly simulations. So that's great, and that's a capability that we will be bringing into CHM. So quite exciting as we move forward to that. And you know how it goes, right? Once you have one continent, why don't you do them all? There's only a few. And so once we sorted out North America, I can easily see us doing South America, Asia, Africa, Europe, and as we add Glacier Components, Antarctica. So I guess we'll do Australia, New Zealand too, just to keep Martin happy. So the workflow is going to be crucial with those sorts of ambitions. So it's Summa workflow separates model-specific steps and model-agnostic steps. And so having these agnostic steps are going to be very, very useful here. The model configuration time costs lean heavily towards model-agnostic tasks, and those are in gray. And that's what we can speed up and make available for CHM. So this generalized workflow we've seen here has reduced configuration times for Summa and Mizu route, and we can use this for CHM as well. And that's going to be very important moving forward. So as we look at community modeling, where we have these model agnostic steps, we set them up and we can run any model in there, including CHM. And this involves looking at specific input layers that we can bring forward, an output layer that's model agnostic, processing layer, another output layer, specific processing layers, and then finally specific outputs. So there's a bit of an iteration from that. And the paper describing this is upcoming by Woter and Martin and other co-authors, showing how they did this with Summa and Mizu route. So that's great advances coming on the hydrology, and I would think by next year we'll see this in full functioning formulation with many variations and taking advantage of those Summa workflows as well. But we have the challenges of the Canadian prairies, and the Canadian prairie hydrology is often seen as some of the most challenging in the world because of the level topography, the post-glacial aspects of that topography, and that regular river basins have not formed. Geomorphological processes have been dominated by glacial and post-glacial conditions, not fluvial geomorphology. And so we have to deal with surface depressions and very low hydraulic conductivity substrates under the soils, which permit very limited connections with the deeper groundwater systems and subsurface systems. And so it's not quite bedrock, but it's close to it sometimes with the glacial tills. And so Kevin Shook has been working on solving this problem for the last decade with various models that have been developed over time. The wetland DEM ponding model, WDPM, and the pothole cascade model are two principal ones in there. Pothole cascade model has been brought into CRIM before and is a crucial aspect of the cold regions hydrological model, but these models are computationally expensive. And so the hysteretic and gatekeeping depressions model is an attempt to calculate the variable hydrological roles of depressional storage and water transmission, which controls the connected fraction of the basin that's connected and able to produce runoff, and the contributing fraction of the basin, which is actually producing runoff that can make it to the basin outlet. So the parameters all have a physical meaning, and there's a paper that was published this year to describe that. And let's go into it a bit. How does it work? Well, it calculates different connected and contributing area fractions caused by two types of storage: large depressional storage and small depressional storage. So small depressions show hysteresis, but not gatekeeping functions. What is gatekeeping? Gatekeeping is where a large wetland, if it's not full, blocks the transmission of water out of it. If it's not spilling, then anything happening upstream of that wetland does not connect to the river basin. If that big wetland gatekeeper is full, then it can connect everything through. So it's like throwing a switch in here and to connect the circuit. And so those large depressions are very, very important. Ross Phillip first came up with the gatekeeping concept, working up in Baker Creek with Chris Spence and myself. But the smaller depressions show some hysteresis, and we'll explain that in a bit, but not the gatekeeping functions, can be dealt with differently. So we can have explicit solutions for large gatekeeper depressions and more statistical solutions for small depressions. So let's dive into it now. The relationship between water storage and the connected or the contributing fractions are hysteretic. And that's an important complexity that we have to deal with in these models to get prairie hydrology right. Without it, we've had model failure after model failure for decades in the region. Of course, after the wetlands dry out, the contributing connected fraction and hence the contributing fraction is zero because depressions are below their sill levels where they can spill. It's what we call Spencean fill and spill. Chris Spence first identified it years ago. Many others have worked on it, Jeff McDonald and many others, but it's the key process here. So refilling these depressions differs from the initial filling because they empty differently from their filling, and that's where we get hysteresis. Now, this is what it looks like modeled with two different models, but as we add depressional storage by adding water to a prairie basin, I use the word basin loosely, we'll call this sub-basin 5. So it doesn't have many large depressions, so we add it, and we get a fairly linear relationship between contributing area and depressional storage. Okay, that's fine. But as soon as we start taking water out through evaporation, or it can be percolation down into the subsurface, then we get a slight decrease in depressional storage fraction, but a collapse in the contributing area. It drops down quickly to zero. And usually we're moving somewhere within this triangle in some unvirtuous circle or series of cycles, depending on the wetting and drying of the prairies. And of course, given the extreme climate, that's a big impact. So these are filling curve simulations, 10,000 realizations of a basin with 1,000 depressions. And as you can see, that's based on Pareto distributions of depressional areas and a copula between depression and basin areas, and show you some of the types of cycling that we can get within that hysteretic relationship between depressional storage and fractional connected area. So we can linearize this and come up with a linear hysteretic model, which it has the model states set. In this case, the contributing fraction, or connected fraction, and the full fractional water volume are the two states. If we go from an initial state of A, we can remove water to be a little bit of water from it, and it without much change in the fractional water volume, we can lose much of the connected fraction. If we keep removing water till we end up with C, we can lose now more fraction. Now we're seeing substantial fractional water volume declines, but we're still disconnected. The connected fraction is zero. Then add a little bit of water. Fractional water volume goes up a bit, but all of a sudden we're connected back in the basin. So that's an example of that linear hysteretic relationships that we can follow with this type of model. Now the gatekeepers, the large depressions, they might fall outside of the Pareto distribution. And so if a largest depression is greater than 2% of its area, then we consider it to be a gatekeeper. And it's the degree that it can gatekeep depends where it is in the basin. If it's in the upper part of the basin, it won't have much of a gatekeeping function because there's not much upstream of it. Its potential contributing area is quite small. If it's downstream in the Prairie Basin, then the whole basin is gate kept by this one. So anyway, when we model them individually, we do not see this hysteresis in their behavior. And these are different pothole cascade model simulations of the effect of location of one large depression in the basin, and putting it in different areas and its areal fraction of the largest depression going from smaller up to larger. And this is the area above or upstream of the largest depression. So everything's upstream. The big gatekeepers down at the bottom of the basin, 0.5, it's up near the top of the basin. And we can see we get very different impacts on the hysteretic relationship with this. If the largest depression is small, then where it is in the basin doesn't matter very much. But when it's large, and we're getting up to 0.3, then where it is matters quite a bit as to the relationship between connected fraction and depressional storage fraction. So that large depression model, we can view it, conceptualize it as this. It's a pond. We have direct precip on the pond, runoff from the pond's basin, and then we have an immediate basin around it. But then we also have a basin above that large depression that connect to it, and then part of the basin that's below this. And we can also imagine regions without small depressions that we can exclude from this. And so we have flow from small depressions above it, and then it's also realized there are flows below it. So putting this together in HDDM, we have an outlet that's fed directly by the upland land areas with, and these have small depressions in them that feed in, but that upland and the small depressions also feed into the gatekeeper, the large depression, which then controls some of the flow to the outlet. So the gatekeeper is partly bypassed, but not completely bypassed. And we can set it to different things depending on what we can measure about that basin. So the upland goes to small depressions, large depressions, and the outlet. Small depressions go to the flow to the large depression and the outlet. The large depression only contributes to the outlet when it's filled. So state variables, small depression storage depth, connected fraction, large depression storage depth, and a variety of parameters that we have to measure, including volume, area, scaling for this. So I'm going to jump through quickly here. These are some of the functions of HDDM to calculate the fluxes to the small depressions, calculate the connected and contributing fraction, add or remove water from the large depression via different hydrological processes, and calculate the current areas of water in these, and then its functions are to route flow amongst the units. We've added HDDM to different models. Mohammed Ahmed has added it to mesh and to hype. We've added it to CRIM as a macro, and of course, we need to test and validate that. The CRIM tests with it are quite encouraging. This is for Smith Creek over different years. We always have trouble with 2011 because of various problems, but in the years where we have more reliable measurements and simpler situation, it's able to do quite well in there. And you can see the hysteretic relationships in the various sub-basins of Smith Creek. Smith Creek's about 400 square kilometers in eastern Saskatchewan. When we compare the CRIM using PCM, which is a more complex 46 wetland representation of wetland network dynamics, to the simpler HDDM, we get almost identical results through their over a multiple year run at Smith Creek. Okay, into groundwater, and we'll move to wrap up soon. So groundwater is going to be incredibly important for this. Joseph Lukili has been looking at this and dealing with this in terms of both equilibrium water table, which is a first order solution where we have a simple mass conservation over control volume, and dynamical water table as well. And so we're going to need to couple the surface water dynamics to this groundwater system. It will need to be a two-way coupling, and that's where we're headed with this. So I'll detail some of the thoughts here as he has examined the mod flow system as a possible component into CHM that would couple in at the bottom of Summa or whatever the soils are in CHM at that time, and then provide a two-way coupling back up to that system as well. So a bit of overview on mod flow. It has a finite difference and control volume finite difference approaches. It's capable of coupled surface groundwater solute transport, variable density flow, and groundwater management. It has many variants that are out there that I won't go into it, but mod flow 6 is the one of interest to us, and it has different packages for initial conditions, hydraulic properties, stress constants, head boundaries, and then interfaces with wells, streams, drains, evapotranspiration. The ModFlow is able to handle structured and unstructured grids of various types. And so that's very attractive for us, given the unstructured grids that we sometimes use in CRIM and in CHM, but also we're able to have ModFlow grid cell structure that's different in the subsurface from what the surface is providing, and that will be where we link the two. So if we look at CHM as something that's bringing all these things together from Summa and ModFlow and Mesoroute, this is a wonderful conceptual diagram of where we're going with these various components here. And so ModFlow itself will be coupling strongly with Summa as an initial land model through here to give us shallow and deep water table dynamics. And Joseph has, so this diagram is quite nice, and it's really nice conceptual one for where we're going. It's a new horrendogram or a horrendogram. Anyway, and the experimental design domain for groundwater coupling, we're going to start off initially in the Bull River, Upper Bull River area to get things working there. So, okay. The Snowcast, I'll just wrap up there because Snowcast is the applied part of CHM, and it's had tremendous improvements. I strongly encourage you to get on to snowcast.ca and take a look, play around with it. It's forced by 2.5 kilometer HRDPS Environment Canada forecast from the GEM model. It's applied over a very large domain, 186,000 square kilometers. It's bigger than many countries. It's applied down to the snowdrift permitting scale of 50 meters and has 300 million raster cells that are reduced to only 5.5 million triangles. So new site design, interactive map. We've enabled the blowing snow and it's running in Copernicus. And we're going to be working to find new ways to visualize the very interesting cornucopia of information that's coming out of CHM in Snowcast. But you can see the 2-day snow forecast right down to the US border and up to the Wilmore Wilderness in the north, and from Strathmore, Alberta to the Okanagan in the west. So covering a large area already. And as you zoom in, you can see the snow redistribution over the mountains, the scoured ridge tops and the drifts and avalanche formations just below those scoured ridges, and then the valley bottoms. Here's the number one highway recently, where it's had much warmer, rainier weather than the high mountains where the precip has fallen as snow. So getting the phase right is crucial for that precipitation here. And Awas has been working with Chris to look at application of this in the Pyrenees, along with the research group of Nacho Lopez Moreno in Zaragoza in Spain. So this is a process-based evaluation of the processes. We have lots of data in the Ethos catchment in the Pyrenees of Spain, setting it up with variable spatial resolution meshes. I've been there. It's a beautiful and really interesting site where they have excellent data to test this with from their UAV snow depth maps over multiple snow seasons. And they have good logistical access to this basin as well. So it's a good one run by the Spanish government, and we'll be working there and then applying this over the Pyrenees. So that will be exciting. So the outlook for Snowcast is improving the visualizations, adding the 6-day GDPS forecast to it as well. Use 1 kilometer GEM in Western Canada. Data assimilation, Zabang is looking at this for assimilating remote sensing and surface snow data. Expand it to North America as areas where GEM coverage is available. Start to move up to those continental scales, starting in the Mountain West. And then extend it to other mountain areas where its capabilities are particularly of interest through our relationships and the Planetary Water Prediction Initiative. So Spain, as I mentioned, but ultimately the Andes, the Himalayas, and Central Asia. And I should note that CHM is an award finalist. Chris? And CHM has been nominated for and selected as a finalist in the Science, Technology, Innovation, and Collaboration Awards presented by the Saskatoon Regional Economic Development Authority. And we'll find out tomorrow at the award ceremony who the winner is. And so it's CHM up against canola. Wow, yeah, we can beat canola. Medical imagery, no problem. Hydrodeal oxygenation catalyst, bit scary. Protein vaccines, COVID vaccines, we can beat all these things. And so Chris and Vincent have done such a wonderful job with this. I have great hopes. So let's go to some conclusions here. I think we're showing that CHM can operationally model snow hydrology in 3 dimensions at multiple resolutions, and we're approaching continental scale areas for water predictions. CHM has good snow capabilities and is now developing the glacier, depressional storage, land hydrology, and groundwater capabilities to become one of the most advanced hydrological models the world has ever seen. And the core team is moving forward on this now, and it is something where we will continue to incorporate the advances in modeling and science, in global water futures and beyond, and be, I think, a superb legacy for the project and program. So I want to thank all the many scientists and engineers and modelers who have been contributing to this advance, and it's an exciting future ahead, I think. Okay, I'll stop there. Thank you.
Thank you very much, John. A lot of material, a lot of interesting development. Some of them hard to digest at this moment, but everything seems to go perfectly under next-gen modeling. And thank you for the presentation. We have some questions for you, John. I think the first question is, yes, Cameron Hossein. How did the triangle mesh of CHM handle routing features like flow direction, flow accumulation?
Okay, yeah. We've had experience routing blowing snow with these using wind direction and flow directions, but with routing in it right now, it's hydraulic routing is not built in, but we'll use the Mizuho route features which have been developed in collaboration with Martin Clark's group, and that I showed an example of earlier on the continental scale where the Mizuho route has been coupled with CHM and is showing substantial advances. So it'll be the Mizuho route features, and that will be able to deal with flow directions and accumulations of flow, including in areas where modest topography.
Yeah, so as a person working with Mizuho route, I can add a little bit to that is Mizuho route routing elements should not really follow CHM. The beauty of coupling is that the CHM elements could be separate from the routing subbasin. So we have a vector-based routing. So let's say we can use different products for the routing, which is merit hydro or based on hydroshed, and CHM can have its own basically triangulation, which various configuration. But it doesn't stop us from matching the CHM with Mizuho route. That needs a little bit of thinking, but that's also possible.
Yeah, I mean, the beauty of having it set up in a model agnostic way is that we can take advantage of where Mizuho routing has been established, which are large areas, and start to immediately plug into that as soon as we have the simulations ready to go.
Exactly. Yeah. I hope that answered the question. The second question we have from Curtis Halberg. Thank you for the update on all the exciting work. Is HDDM parameterized entirely from analysis of a DEM in a GIS environment? There are no parameter to calibrate, or like, is there any parameter to calibrate? If so, what resolution would be needed in a DEM for application in a typical prairie pothole region subbasin? Does it require a LiDAR DEM?
Yeah, so where we've set up and tested HDDM has been in Smith Creek, where we do have LiDAR information, and it's excellent for doing it. One thing that we can do is by taking the calculations from classical areas where we do have good information, we can apply it over larger areas. So we need to know the fraction of the basin that's occupied by small depressions. And so some of the classification of small prairie basins that the Prairie Water Project has been doing can help us with that. We need to know the maximum storage depths of the small and large depressions in the basin. And again, I think basin classification can help us with that. The fraction of the basin area above the large depressions you can pick up from coarser scale remote sensing and even coarser scale topography. So we can locate those using remote sensing products that are already available in there without the high resolution LiDAR DEM. But the basin grid fraction and of that basin area, that's certainly helped by that. And when we use Hayashi and Vanderkamp's area volume scaling for the large and small depressions, and that certainly can be better informed by LiDAR DEM. So I guess the answer is yes, it would be better with LiDAR DEM, but it does not require that because of the ability to transfer parameters from similar areas where we have better information.
Yeah, so basically you suggest investing on LiDAR. That's what I hear.
Yeah, it's ultimately even to work out basin areas in the prairies, things like this. As soon as we get LiDAR, we find that we have an error in estimating the basin area of like 20-30%. And so it's hard to model things when we don't even know which direction is flowing. So LiDAR definitely helps with that. Alberta ag areas are largely covered by it. Manitoba is improving, but Curtis, we do have a gap in Saskatchewan that I think is crucial to fill if we're to enable reliable hydrological modeling of the prairie region. And it's simply part of the basic infrastructure that we'll need to move forward with any model in Saskatchewan at the resolutions that we need for user applications that are important to users.
Yep, thank you very much. Hope we will have that infrastructure soon. And the next question from Jeep Chadori. Do the time step in CHM are governed by current number, or is it fixed time step?
Well, we can vary the time step, so it's depending on the models. So
the time varying time stepping in the simulation, right? For example.
Yes. Yeah.
Okay. Perfect.
Yeah,
and the next question from Martin Clark. The next gen advances are impressive. How do you see these advances being integrated in models that are developed and used by GWF partners in provincial and federal agencies?
Yes, well, this is a very interesting question because there's, of course, it's not a simple thing for provincial or federal agencies to change their technology rapidly. One thing, though, is that, and as an early step, to have Snowcast available over a larger area would be a way to provide more reliable snow information that provincial agencies could ingest immediately in their prediction systems and forecasting systems, which have large human elements to them as well. But then further, one could use it also to update the states of hydrological models that exist. And then further down the road, as we develop this into a reliable multi-scale system, to take advantage of the routing. So particularly where mesh is set up with vector-based routing, then that's something we could start to plug into there. And so Saskatchewan has looked at that, of course, over these areas, and Yukon has got that as well. And so as we update to vector-based modeling, then we can plug in more easily. And then with federal systems, this is done in collaboration, of course, with Environment Canada through the help and work of Vincent Vionnet. But we are coupled with the GEM forcing data right now. But this shows a way to move forward with the large federal flow advisory systems that are being developed in Environment Canada, and give us a way to develop partnerships that could take us up to global water predictions, and but certainly the most advanced predictions on the continent And so I see tremendous advances there through our partnerships over time.
Excellent. Thank you very much for the answer, John. We have another question from Wouter Kenoben. Hi, John. Have you got any thoughts on the extent to which our currently available computational infrastructure is ready for these next-gen modeling efforts? To clarify, I am thinking about available hardware, computing power, software support, etc. I think software support in the sense of software and the expert who will probably help with.
Yeah. So this is, Chris Marsh has worked very, very hard in getting CHM to work properly in the Copernicus system, which is our GWF supercomputer that we have at the University of Saskatchewan. And so that's really the system to move forward with right now. And it's a new system, so there are bugs in it. And Chris and the comp sci team had some big battles, months-long battles of roadblocks in terms of getting things to work properly, ghosts in the machine type issues over the summer, which are there, but they battled their way through that. And so, which is very, very promising. It's also kudos to them for doing that. And so I think we've got the systems in place to apply this efficiently on that Copernicus system. The question will be, as we go to continental global scales, is Copernicus big enough? And the answer is no, it's not. So we will have to be investing in improved computer power in the future as we move on with these systems. But certainly for the projects that we have now and moving up to much of Canada, we can probably do this within the Copernicus system. Yeah. It'll be interesting to see how we break it. Compute Canada, that's another matter. And there remain some roadblocks in inefficiencies there in running things which are continue to be somewhat problematic at times.
Yeah. Thank you, John. Is there any other question? Any last minute question? We are getting to the top of the hour. So it seems not. I would like to thank you, John, for the great presentation you gave. Very exciting. And I would like to thank all the participants. I would like to remind you that the next webinar of this series will be on 13th of January. Trish Stadnik from University of Calgary will give update on the advances in water management theme. So hope to see you there, basically. And because we are in the last months of the year, so I would wish you Happy New Year and Merry Christmas if we don't see each other. The recording of this meeting will also be posted on our core modeling website soon, maybe today or by tomorrow. Thank you very much. John, do you want to say anything or?
No, just thanks to my co-authors on this. The scientific advances they've made are profound and really exciting. So it'll be fun, and we'll continue to grow this next gen team as we bring more elements into it. This is the future, and we can make this future. So it's kind of fun. It's like I say, this is the part of GWF where I'm just smiling all the time. So thank you.
Perfect. Thank you, everybody. Have a nice rest of the day. Bye.
Bye then.